Welcome back. And now we get to the last video where we put everything together. What you'll want to do before you begin to watch the video is make sure that you have the two data sets for the F-16s and the home run data set we used previously downloaded and imported into StatCrunch. So what have we been doing in this module? Well, we've been talking about how we get information from data. And this process is called exploratory data analysis, and it consists of 4 steps. And so far, we've done the first 3. So we've talked about how to inspect and clean a data set. We've talked about how to plot a data set, the different types of plots we have with quantitative variables. And finally, we've talked about different summary statistics. These are statistics, things we compute from a sample that are going to capture the important features of the plot. And last time we found out that those 2 features are the center of the data plot. We want to know where most of the data points are centered around. And then we also want to know the spread, because the spread is going to tell us how representative the center is if we take one particular individual from that sample. But now we're going to get to the point where we put everything together and we're going to describe the plot. So we're going to take the information in video 2, and this should be video 3. We're going to take the visual summary, the numerical summary, put them together, and now we're going to learn how to describe data from a quantitative variable. One issue that students very often have is when they're asked to describe the plot or data from a quantitative variable, they kind of go freestyle. They just give their impression of what they think the data looks like. However, in statistics, when we're told to describe data on a quantitative variable, we always report 5 specific things. And they are, first, the number of modes, or the number of local peaks in the data. And we're going to discuss in a minute what that means exactly. The shape. We discussed briefly in the last video the difference between skewed and symmetric data and why it was important. And outliers. Outliers are probably one of the most misunderstood aspects of statistical analysis. So we're going to spend some time talking about what they are, what we do with them, and why they're important. And the last 2 we already considered in the last video. We talked about how we describe the center of the data set and how we describe the width of the data set numerically. So let's go ahead and we're going to apply this description to our F-16 data. We're going to see how we can describe it, giving these 5 pieces of information. So let's first of all look at the number of modes. So a mode is considered a local peak, and the number of modes, which is what we want to report, is going to be the number of local peaks. So for example, you can have a plot where there's no mode, there's no peak. In that case, we say the data has a uniform appearance. Notice you might think that this little blip here is a peak, but it's not. It's just random variation in the counts. If on the other hand, we have one peak, which is occurring right here around, I suppose, 4, one peak we describe as being unimodal. Una meaning one, like unicycle or unisex, and modal meaning mode. So unimodal, one mode. And again, you have to make this distinction between having one peak and 2 peaks. You might think that this peak around 8 or 9 is actually a mode, but it's not. And the way that you can tell that is if we go back and we remember in video 0, the purpose of these plots, we're trying to fit this choppy sample data to a nice smooth curve through the population. So I'm trying to find a simple, smooth curve that kind of evenly cuts through the data. And you notice that a single mode does the trick, whereas two modes is making the analysis a little more complicated. This looks like a blip pretty much just due to the random sampling. We can have situations where we have two modes or two local peaks, as we see here. And just like unicycle, we can have a bicycle, right? Two wheels. And so we describe this as bimodal, two modes. When we get to more than two modes, we don't get into trimodal and tetramodal and all that. We call it multimodal. And it's not particularly common in statistics. Now, why do we care about the number of modes? So to kind of illustrate this point, this is data that I plotted, and we're looking here at the average drive of all professional golfers from the year 2008. So every single golfer, I took all of their drives, I averaged them, and that was my single data point. And then I went ahead and collected all of the averages for all the players, and I plotted them. And you can see clearly from this histogram, this is bimodal. There are easily two peaks. And the question is why? What is it in the data that's causing these two peaks? So the reason why the number of modes are important is because modes can often represent subpopulations in our data that we'd like to be aware of. So what might these two subpopulations be? Well, the key is to realize the word all professional golfers includes men and women. So this lower peak here is probably due predominantly to the women golfers. And this upper peak probably consists mostly of male golfers. And we would want to know this because I have to consider whether or not I want to do the analysis with both of these different populations in here. So you might ask yourself when this might occur in marketing and medicine. For example, we know that different sort of ethnic groups have different responses to COVID-19. So if you looked at the antibody response for maybe whites and blacks, it might look something like this. Now, one thing I will say is that very often there's more than one population and you can't detect them. And a classic example is men and women. If you look at the variable height and you go back to 1950s and you were to make a histogram of heights from a population containing both men and women, you would see this sort of bimodal distribution. Women were considerably shorter than men, but women are catching up. Who knows why, right? But they are. And if you look today, and I just saw an article about this a couple of weeks ago, if you look at the height distribution of a population containing women and men, the peak is no longer, these two peaks are no longer discernible. They're so close that the peaks overlap, and what you see is one really broad peak in the center. And so sometimes you won't see a difference. But in that case, it means that it's probably not a major factor, right? You can include both populations. So one of the quiz questions, this is the F16 data where we're looking at the number of accidents. We plotted this before. How many modes would you say that our data has? Would you say that it's uniform and it has no modes? Unimodal, it has one mode, right? Bimodal, two or more modes, or multimodal? Next, we want to talk about shape, and we touched on this briefly in the last video. And again, just like we sort the number of modes in a kind of rough sort of way, we also kind of classify shape in a very rough sort of way too. There's only three possibilities. Notice that shape only makes sense when we're talking about a unimodal plot. So these are the three basic shapes that we have. And essentially, we say that a plot is either symmetric, meaning that there's a line of symmetry and it's pretty much a mirror image, or I could take the plot and fold it over and it would pretty much superimpose, or it has a tail. So you can see this data set has a tail on the left, this data set has a tail on the right. And so when we describe them, for example, we would say this data set is symmetric. However, if we have a tail, the way that we say tail in statistics speak is we say skew, and we report which side the tail is on. So if we had a data set where the tail was on the left, we'd say it was left skewed. Okay, it's left tailed. And similarly, if we have a data set where the tail is on the right, we'd say it has right skew. Now, one of the things to realize is that very often data sets that are symmetric don't appear to be exactly symmetric. It's very rare that you will get a plot of a data set and it'll be exactly symmetric. And if it is, you have to wonder whether or not the data was fabricated. And so what we're really trying to do is really classify what does the data look most like. Does it look more like it has a tail or more like it's symmetric? This is kind of a rough sort of classification. Now, all of these distributions occur in real life, although left-tailed is really not that common. Symmetric distributions occur a great deal when we're looking at physiological measurements. So, in other words, measurements that we make regarding our body. So things like height, blood pressure, IQ, they tend to be symmetric. We're going to see later on in the course that the symmetric distributions play a very major role in statistics. Left skewed data occurs very rarely. You don't see it a great deal. Notice what's happening with left skewed data. You have a lot of data values that are bunched up near the upper end of the scale. So for example, when you look at SATs at top universities, in fact, I have a data set that contains the SAT scores from the entering class at Harvard. What you see is a distribution that looks like this, right? The vast majority of students have SAT scores over 760. This is with the old scale. And very few students have SAT scores in the 500s or 600s. If you look at the age of retirement or death, right? A lot of people tend to die when they're older, not as many when they're younger. And again, if you look at performance among any class of elite people, where larger is better. Okay, so if you look at long jump distances of Olympic athletes, most of them tend to be really tightly packed here at the top of the scale, and there's only a few that perform poorly. Most students think that data tends to be symmetric, but the reality is a lot of really important data sets are right skewed. And in fact, when you look at income, okay, when you look at productivity, lifetime of products, all very important things in marketing, these are all right skewed. One thing that's really nice is that sometimes when you're plotting a histogram, it's not so easy to tell if it's skewed or not. But you can also plot a box plot. And a box plot happens to be very good for determining if something is really skewed. So for example, if we have a data set where it's symmetric, even though there might be a little bit of a tail here, when we look at the histogram, what we see is we see that the median is in the center of the box. However, when we look at a skewed data set, we see that's not true. When it's left skewed, the median shifted in the opposite direction towards the right tail because the data is bunched up there. And the same thing for right skewed. Okay, the median's shifted in the other direction towards the left. So first of all, if we have a symmetric data set, the median should be near the center of the box. The other thing we can do is we can look at the whisker length. So again, notice that for a symmetric data set, the whiskers are kind of the same length. Again, they won't be exactly the same. However, if we look at a left skewed data set, we can see what's happening. We're stretching out the left-hand portion of the distribution, and so the whisker on the left is larger than the whisker on the right. And of course, just the opposite's true if we look at a right skewed data set. Again, we're kind of stretching out that last quarter of the data. So you notice the first quarter of the data is all bunched up. So this part of the whisker is small. But what it means to have a tail is you take that last quarter and you stretch it out. And so this whisker tends to be longer. So this asymmetry in both the length of the whiskers and the position of the median is a really good way to tell if something is really skewed. So I'd like you to take a look now at the plot of the number of accidents, the same plot we looked at previously when we were discussing a number of modes. And now I want you to tell me what shape you think this plot has. Is it more like a symmetric, more like a right-tailed, right-skewed, or more like a left-skewed? Which one does it look more like? All right. Now we come to perhaps the favorite part of this analysis, which is outliers. So outliers did not make sense in the context of categorical data, but they do in the context of quantitative, and they're generally values that are either unusually large or very small. And they can be caused by a lot of different things. First of all, they could be errors. And that's one of the reasons why we generally check out suspect data values, even if they're outliers. The individual could come from a different population. Okay, you might be at a nursing home testing reflexes and measuring the speed of a person's reflex, and there somehow maybe a young person got in the data set. Maybe they were visiting their grandma. And so most of the old people have really long, really slow reflex times. All of a sudden you have this one person that has lightning fast reflexes. But they're probably not from the population in this case that you're interested in. You're interested in the residents of the nursing home, not young visitors. Sometimes the measurement represents a rare event. So for example, if you're measuring people's heights, you could get someone who's 7 feet 8 inches tall, right? It can happen, but it's very rare. But sometimes they indicate the start of a trend. And this is the one that people generally don't recognize. And I want to show you this using the home run data set, okay? So I'm going to go over to StatCrunch for a minute. And let's see, where's the home run data set? It's here. This is the data set that was collected back in the year 1920. And the home runs of every player playing that year were recorded. Again, we would look at the data sets, make sure that they're all valid, and they are. Okay, when we sort them, they are sorted. And let's go ahead and make a plot. So when we plot the histogram of home runs, I will go ahead and plot the mean and the median. We get something like this. And I'm going to make the box plot too. And again, these are just two different views of the same data. And we can see that there's clearly an outlier. So one individual hit 54 home runs, and that was Babe Ruth. And the question is, how do we interpret Babe Ruth? I mean, did he come from another population? Is he an alien or something? No. He's the start of a trend. Okay, in 1920, Babe Ruth was dominant. No one even came close to him. The next highest person had 19 home runs. That was George Sisler. Babe Ruth had so many home runs, he had more home runs than any team combined. However, if you fast forward to 1927, while Babe Ruth is still hitting more home runs than anyone else, it's not that unusual. There are actually a number of people that are hitting in the 40s and 50s. Jimmy Fox, Lou Gehrig, Hank Greenberg, okay? And so Babe Ruth was the start of a trend. And this is one reason why you do not delete outliers. If there is a trend, you definitely want to be aware of it. It's easy to delete Babe Ruth, but it would be very wrong. you could miss some really fascinating history along the way. Now, notice that the mean and the median are about the same. We talked about this before, right? The mean gets pulled out a little bit because of the outlier. Now, here's an interesting question. What about all these people here? The box plot suggests they're outliers. They're not. And this is one of the reasons why making two plots is always a good idea. The box plot indicates they're outliers, but what is an outlier? And this is where you have to be careful. An outlier is a value that's really separate from the rest of the population. It's like an outcast, right? Babe Ruth looks like that. Okay, these are all the other players. They're all grouped together, right? There's a continuous progression here, and then a huge gap in Babe Ruth. So what's actually happening is we have a really long tail. This is a unimodal right skew data set with one upper outlier. And these values are not outliers, technically. They're outliers, but they're what we sometimes call outliers in name only. They aren't actually outliers. They just appear to be using this criteria that we use for plotting a box plot. And that's very important to understand. There are entire books that are written about outliers, okay? There's a very famous book called The Black Swan by Nicholas Taleb, and it talks about these sorts of situations and how we interpret outliers and why they're so important. Okay. And so again, natural tendency to throw them out. Do not. There's only a few times when you can throw out an outlier, okay? When it's invalid, but then that's really an invalid data value. It's not an outlier, but you might have to it might be really large and suspect, and you check on it and you find out that it's invalid during the process of investigation, a measurement error, or not from your population of interest, okay? But if you can't convince yourself that the data set is bad in any of these three ways, you have to leave the outlier in. And again, just like we said before, if there are suspect data values, we generally do our analysis with and without it, and we report both results. So I want you to look at the plot here on the left. These are the number of accidents in the F16 data set. On this left plot, do you see any outliers? Okay. Well, that is the end of this video. I hope you enjoyed it, and now you're ready to start the homework, and you can go ahead and describe data sets.